All right, what's up, everybody? We got another installment here today. Tried to get this thing to go, to get up and running earlier today, but we were having some network issues at work, so I decided, hey, I'll just come home to the office and do it from here. So, what I kind of wanted to get into today was just dealing with the chemistry chapter. Some of you who you take anatomy and physiology, you've probably noticed that for some of you, your instructors have been adding the chemistry chapter in. They kind of blindsides a few people because they're thinking they're about to sign up for anatomy and physiology, and then they get hit with this chemistry chapter the second week or second day of class. Um, Anatomy and physiology is kind of this misnomer because you're going in thinking, oh, I'm just learning about the human body. And you fail to realize that in order to understand anatomy and physiology, you really need a little bit of understanding in biology, chemistry, biochemistry, a little bit of cell biology, a little bit of molecular biology, and a little bit of genetics all rolled into one to really grasp anatomy and physiology. So what I want to do is I want to make two installments. The first one is going to be a brief overview on some really, really, really basic chemistry. So if you're watching this to try to pass your organic chemistry 324 midterm exam, this is not the lecture for you, okay? This is, hey, I don't understand chemistry. Can you kind of tell me some extreme basics about terminology in chemistry? We're not going to be putting any formulas together or anything like that. I hate to disappoint you. If you do want to learn more about chemistry and you're watching this video on Google Plus, you need to subscribe to Google Plus Chemistry. Google Plus Chemistry is really good. It's a really cool community. I actually subscribe to that community on Google Plus and hit you off with all types of cool information about chemistry. None of that boring stuff that you were probably getting back in the day, but instead application. One of the articles that I was reading on Google Plus Chemistry today was about a group of students at North Carolina State University who developed a new nail polish for women so that it can detect date rape drugs. So that girl could have that fingernail polish on her fingers. Um, she's wondering if this guy slipped something in her drink, and so she can take her finger and stir it in the drink, and it'll change her finger, change the color of her nail polish, and that'll let her know that this guy is trying to slip her a drug so that he can possibly rape her. So it's got chemistry stuff like that. Really, really cool, really applicable, really relevant, really ahead of its time and above the curve. So you'd like that. So without further ado, let's go ahead and get started and talk about chemistry in this reference to anatomy and physiology, just basic chemistry. What you need to understand is that you got to understand some basics about chemistry because of the levels of organization. Now, if you're taking anatomy and physiology, you already understand, or you've at least heard of at least once, about the levels of organization. The largest level of organization would be an organism, which would be myself and yourself. You and I, we are organisms. But as an organism, I am broken down into 11 organ systems, like the digestive system, the integumentary system, the reproductive system, the respiratory system, the cardiovascular system, the lymphatic system, the skeletal system, all these different systems. There's 11 organ systems, and each organ system is broken down into a group of organs. And then when you look at one individual organ, you'll find that that organ is made up of two or more types of tissues. And then out of the four classes of tissues, you'll find that a tissue is nothing more than a collective group of cells working toward a common goal. And then out of this collective group of cells, you can find that there are different types of cells that go into making a collective tissue. And when you select any one of those cells, you'll find that inside the cells, they have little cellular organs that we call organelles that are working inside that cell help that cell do the things that we pretty much take for granted every day. Uh, but when you look inside the organelles and you look inside the cell, you'll find that there are a lot of processes happening inside that cell that you can't really put your hands on. Um, there are structures inside the cell that are working, they're producing things, they are using catabolism and anabolism, which when you put the two together, they make metabolism, the breaking down of substances and the building up of substances. And these substances happen to be chemicals. They happen to be compounds. They happen to be large molecules, some of them small molecules, and these molecules are made out of atoms. And a lot of what's going on in your body is happening on a chemical level inside of cells. When you talk about cancer, the reason why cancer research has had to be so broad, and the reason why there's been so much to go into cancer research, and so many resources, and so many people, and so much time going into cancer research is because how far we go in cancer research is dependent upon how much we understand on the cellular level on down. What we look at as a family member or a concerned friend is a sign or a symptom that's on the organism level. But what's really taking place is something that's happening on a cellular all the way down to a chemical level. And when we can understand what's happening on a chemical level, that's when we can ultimately, truthfully begin to create cures, and at least be in a progressive manner. So it's really important to understand the chemical level of things. For example, you got a person and they got an upset stomach and they're dealing with acid reflux. Well, if you don't understand chemistry behind that, you won't understand the psychology of it, the study of the cells there, and the histology, the study of the tissues, won't make any sense to you. So you got to understand some basic chemistry. So that's what I'm going to do today. I just want to really tackle some basic key terminology that you hear all the time in anatomy and physiology, and kind of debunk a few myths. So let's get started. Let me pop open some notes here. And first, let me change the view so you guys actually be able to see what I'm going to be opening. There we go. And I'm going to go ahead and get this PowerPoint up. And here we go. So you'll notice that in the screen it talks about atoms, ions, and molecules, and the fact that at its simplest level of organization, the human body is composed of chemical structures, which, remember, I just talked to you about the levels of organization, so that's nothing new. However, we're running into some problems here. Stuff doesn't want to move. Let's see what's going on. Seem to be having some technical difficulties. I think this happened to me earlier today when I was trying to record this. Here we go. Now, just for argument's sake, let's make sure that you guys are still there. Okay, good. We're still good. We're still good to go. Okay, I'm just going to kind of show it from this perspective, just in case. I don't want to lose you guys. So let's go to where I want to go. Here's the thing that people need to understand. All right, when we talk about the human body, and you're talking about the human body from a chemistry or a chemist standpoint, a chemist is going to refer to the body in its basic substance, which is what we refer to as matter. The human body is made out of matter. As a matter of fact, everything around you is composed of matter. And matter is always going to be in one of three forms. It's either going to be solid, a liquid, or gas. Now, if you talk to an astronomist, if you talk to somebody in astronomy, then they're going to probably throw some extra things in there. But we're just talking about the human body, and we're keeping this real basic, no major theories to go into this. The human body is composed of matter, and matter comes in three forms when it concerns the human body: solids, liquids, and gases. And if you look at that image over there to the right that I politely borrowed from NASA, the Glenn Research Center, you'll notice that there are three phases of matter. Solid substances, they always hold their shape, and they have pretty much a fixed volume. In other words, if I took that block and I put it on the table and we decided to come back next week to look at the block would still have its same shape and it would have a fixed volume. It would still be the shape of a block. Whereas if that block took the form of a liquid, then it would not have its own shape. As a matter of fact, a liquid will take on whatever shape of the container that it happens to be in. So if the container is the shape of a block, then the liquid will take the shape of the block. If the container is the shape of a circle, then the liquid will take the shape of a circle. And it also has a fixed volume. If I pour that liquid into that block and I shut it and I close it and I put it on the table and I come back a week later, its volume is pretty much going to be the same as long as I don't, introduce that liquid to a different environment or different specific outside influences to purposely change its volume. Without those things coming in from the outside, its volume will remain the same. And if we change that liquid to a gas, then it will not hold its own shape. It will ultimately take the shape of the container. Also, it will take on the volume of the container. Now, it won't have a fixed volume. Okay, a gas can expand. It can expand and it can take on the volume of the new container that you just put it in. If I had a gas and I forced it into a 16 ounce bottle, then it would take up all 16 ounces of the bottle. But then again, I could take that gas and I could pour it into a 8-ounce bottle and it would take up 8 ounces of space. We just went from a 16 ounce, but we can now go down to a 8 ounce. Whereas with a liquid, if it was 16 ounces of liquid, that's it. You're not going to squeeze it into an 8-ounce bottle. And when we look at matter, whether it's a solid, a liquid, or a gas, when we look at matter, the smallest functional unit of matter would be the atom. And an atom is literally the smallest thing you can get of any element. So basically, if I took a piece of gold, I could get all the way down to the level of the atom of gold. But I couldn't get any smaller than that, because if I got smaller than that, it would cease to be about the properties of that element. It would be all about those subatomic particles, those neutrons, those electrons, and those protons. So as long as I take that element, that sodium, that chloride, that copper, that zinc, that gold, that silver, that nitrogen, that carbon, that oxygen, that helium, whatever that element happens to be, regardless of the element, as long as I don't go any smaller than an atom, I'm still working with the same substance, maintaining the same properties of that substance. And that's why an atom is so important. It's kind of like buying a bag of sugar and pulling out one granule of that sugar. As long as you can pull out that granule of sugar, you can put it on your tongue and it will still taste like sugar. Once you get smaller than that granule, once you get down to like a level where it can't bind to your taste buds, so that it can't stimulate the area of your brain to recognize it as sweet, then you've gone too far. It's gotten too small. So when we look at an atom has 3 subatomic particles that make up an atom. You got protons, neutrons, and electrons. And protons are the positive charge on an atom. Neutrons don't have a charge, henceforth the name neutron. They're neutral. And electrons have a negative charge on them. And protons and neutrons sit inside the atom. They create what's called a nucleus, while the electrons actually orbit the nucleus itself. The electrons are negative, and they orbit the nucleus of the atom. And the electrons are important to remember, because if I have one electron and I have one proton, the two of them are going to cancel out one another. It's kind of like having a dollar and then somebody comes up and says, hey, can I borrow $1? Well, you don't still have $1. You don't have $1 at all now. So that positive and that negative make it neutral. No, you don't have $1, but then again, you don't have an extra dollar, and so you don't owe anybody $1. So you don't owe anyone $1. You don't have $1. And you've already given your $1, and you're not receiving $1, so that makes it neutral. Now, this is where things get a little tricky. If you understood that, if you didn't understand that, you can always rewind and go back. But I want to kind of move forward, and I want to play with something here for just a moment. One of the things that you want to keep in mind is that an atom is not going to always remain an atom forever. Sometimes we take that atom and we attach it to one or more atoms, and then we create something called a compound. Generally, the compounds that we generally talk about are like the ones that you see in the image there in the slide. Water is a chemical compound. Um, Ammonia is a chemical compound. Carbon dioxide is a chemical compound. Hydrogen peroxide is a chemical compound. You'll notice that they contain two or more elements. Water contains the element hydrogen, and it contains the element oxygen. And those atoms of that element are connected together and they become H2O, commonly referred to as water. We have two atoms. Uh, we have two elements present in carbon dioxide. You have one atom of carbon to two atoms of oxygen, and that creates carbon dioxide, and then so forth and so on. When we talk about a molecule, sometimes it gets a little confusing, and we're not going to get too deep into that because you can start arguing over the difference between what's a compound and what's a molecule. But for all argument's sake, we're going to talk about ionic compounds and molecular compounds. And what you're going to find is that a molecule is nothing more than two or more atoms that you join together chemically. So a lot of times you'll hear us flip back and forth between compound and molecule. I would go so far as to say that usually in anatomy and physiology, we will refer to something as a molecule. Most of what we'll talk about will be molecules. Sometimes they can be classified as both a molecule and a compound. And in our case in class, we'll try to be specific about which one is which, but a lot of times they'll be the same thing. Now, I need to take a minute to talk about what an ion is, because I started jumping the gun. I started talking about molecules and compounds and the fact we can stick atoms together, and I'm getting ahead of myself. I need to slow down for a second. The reason why atoms can stick to one another is because of those electrons. And generally, there's two ways that we're going to talk about that you can get two atoms to stay connected to one another. Number one, if those atoms share their electrons, and number two, if their opposite charges attract one another. So those are the two ways that we're going to make these compounds, that we're going to be able to make these molecules. If the two atoms need to be connected to one another because they're sharing electrons, or if their opposite charges attract one another. And let's talk about the ones where their charges attract one another. In an ionic compound, that involves two ions. Now, what's an ion? An ion is nothing more than an atom with a charge on it. So an atom can have a negative charge, or it can have a positive charge, or it can have no charge. If an atom has no charge, it's an atom. But the minute that we give it a charge, whether it be negative or positive, it then is reclassified as an ion. And that's because it either lost some electrons or it gained some electrons. Either way, it's now changed the charge on that atom. If that atom is sitting there and it has neither gained nor lost electrons, then it's fine. It is what it is. However, if that atom gains an electron or loses electron, then it winds up having a charge on it. And you can see in this image that an ion, an atom with a charge, is used in a lot of different places in your body. Notice that you use sodium ions to make electrical signals for neurons. I mean, the neurons, 97 to 98% of all the neurons in your body are in your brain. So they found with an experiment that if they plugged up a 10-watt light bulb to the human brain, that 10-watt light bulb would light up because there are so many signals, electrical signals being sent back and forth by those neurons in your brain that they generate just enough electricity to light a 10-watt light bulb. So that's a lot of juice going out there, and they use positive sodium ions. You use positive calcium ions to help create blood clots and to help muscles contract. As a matter of fact, without calcium ions, your muscles won't contract. And when I say muscles, I'm talking about skeletal muscle and cardiac muscle. You know, those muscles require calcium to do their contractions and to function on a regular basis. And last but not least on that list is a chloride ion. And the chloride ions, you use those in the stomach to make hydrochloric acid, HCl. So you add a hydrogen ion to a chloride ion, and then you make hydrochloric acid, which is a stomach acid, and that helps to denature and break down protein in the stomach. When you look at these other tables, you'll see that they list out several different ions, but you'll also notice something really key about this list. This first table is listing something called cations. Do you see that in the far left-hand side with the column? Cations are positive ions. So if you look over here, this table is full of nothing but positive ions. Those are cations. And then over to the right, they show the physiologic significance. I'm sorry, I'm messing words up, trying to talk all over myself. But you got the physiological significances here, these different things that they wanted to point out. If you look at sodium and potassium and calcium are used a lot. It doesn't mean that magnesium and hydrogen ions are not important as well. You'll see these later on. But sodium, potassium, and calcium are ions that are constantly used. Sodium and potassium, you'll learn a lot about them in the nervous system as it's the nervous system and the muscular system, because they participate in generating action potentials. They participate in a lot of intercellular communications, and they also work a whole lot in generating action potentials and helping communications between cells. Whereas calcium ions are, of course, used on the bone and the bones and the teeth, and calcium ions are also used in neurons, brain cells. So you use calcium all the time. Now, if you go to the next slide, you talk about anions, and anions are negative ions. So they are negative ions. Just because there's fewer of them on this table, it does not mean that they're any less important. They just chose these three because these three are three anions that you're going to talk about for the rest of your time in anatomy and physiology. So if you're taking a two-part anatomy and physiology, you're going to hear about these dudes the whole way through. If this is a one and gun anatomy and physiology, then you're going to hear about these guys the whole way through. You can't escape these anions, like chloride ions. You use them in the chloride shift in your red blood cells. The red blood cells use chloride ions so that you're able to transport carbon dioxide to your lungs. An extremely important job. If you don't think it's important, you don't want to be on the receiving end of your body not being able to transport carbon dioxide out. That's not going to be safe. Bicarbonate ions, they actually help to buffer the pH in the blood. It's a really good item to have circulating in your body fluids. And then phosphate ions, they help to harden your bones and your teeth. As a matter of fact, you store some of that stuff in your bones as well. Also, a very important component of nucleotides like ATP, DNA, and RNA. Now, I want to skip ahead to something really quick. Cations and anions, they are opposite charges of one another, which goes back to that old saying that opposites attract. Well, I don't know about all that. They sometimes they do, sometimes they don't, but they definitely do in chemistry. And one of the things you have to understand is that positive ions attract negative ions, and they think they want to be together, but they're in for a rude awakening when they get connected, because they soon find out that, unless they get dissociated in water or some other solution, they're pretty much stuck. Um, so in one example, you can see where salt can be formed due to the fact that sodium is is an ion, and chloride is an ion. See, I'll show you what I mean. You can see here in this table where you have a sodium atom that's sitting over there. He's minding his own business. Now, why is he a sodium atom and not a sodium ion? Well, that's because if you look at these shells, like the purple dot is the nucleus. The rings around the purple dot are shells. So those are shells. Now, any atom worth its weight is going to want to make sure that those areas are full. That's what it's going to want to do. It's going to want to make sure that those areas are full. So that sodium atom, he wants to get rid of that last electron, because out there in that outer shell, he would need like 7 more electrons just so he can make himself complete. And that sodium atom is not going through all that work just to be rejected, as he tries to get like 7 more electrons to go out there. Who's just going to hand over 7 more electrons? Nobody. So sodium's in a bind. Then you got chloride, or chlorine, the chlorine atom out there, I'm sorry. And the chlorine atom is looking, and he's like, okay, I'm confused because I've got 7 electrons and I just need 8 to make my shell complete. But the problem is I got 7 and I don't have an extra 1, and no one around here wants to just loan me an actual electron. Remember, you're going to have to keep a close eye on these two guys, because what they're going to do is this. Sodium looks over and sodium says, look, I've got an electron. Chlorine says, look, I need an electron. The two of them have a discussion, and bada boom, bada bing, what a wonderful thing. You have sodium, who's finally happy because he got rid of that pesky extra electron that was out here. And then chloride's happy because he, in turn, took that third and final, he took that third and final electron and attached it right here. So both of them think that they're just going to be fuzzy fine and everything's going to be wonderful. But what they fail to realize is that you've got these positive things on the inside of the nucleus, and there's a positive atomic structure in here for every negative atomic structure floating around. So if you notice inside this bubble, the 11 proton number has not changed. There's still 11 protons that are positively charged inside the cell in the nucleus. Well, 2, 4, 6, 8, 10. That's 10 positive, that's 10 negative electrons to its 11 positive protons. What in the world is positive 11 plus negative 10? Right, it's positive 1. So if I add a positive 11 to a negative 10, I'm going to get a positive 1. So guess what? This sodium ion is about to wind up with a positive charge. Meanwhile, the chloride ion, he thinks he's just sitting on top of the world, because this dude has 2, 4, 6, 8, 10, 12, 14, 16, 18. He has 18 electrons. And how many protons does he have? Well, if you look in the middle, you'll see that he's got 17 protons. Well, that's 17 positive protons and 18 negative electrons. So you know what? Negative 18 plus a positive 17 equals negative 1. Yeah. So this person who catches this one right here, they're going to look and they're going to say, oh, no, that's not going to work. I just lost out, because now I've got a positive ion over here of sodium ion, and I've got a negative chloride ion, and these two, because he's positive and he's negative, will be drawn to one another and ultimately will attach with one another with a contingent of, a whole group of these guys, and they'll start binding to one another and forming an actual crystal of table salt. So remember, ionic bonds form because you had two ions that were attracted to one another and they connected to one another. You had these two atoms that showed up on the scene. One wanted to get rid of wanted to get rid of an electron. The other one wanted to gain an electron, and so they decided to do just that. The one who wanted to get rid of electrons, he handed one or more over to the atom who wanted to get more electrons, and so they both got their wish. The one who gave was trying to get rid of it. The one who received, he received it, and now there's a whole bunch of people just mad with them because now that they've done this, they can't go bouncing around like they were before. They're now drawn to one another and attached, and they form a bond with one another known as an ionic bond. Now, the second way that we can form a bond between two or more atoms or two or more molecules and join them together for a very lengthy period of time is through covalent bonding. And the thing I want to point out about covalent bonding is all about sharing. It is all about sharing. It's about the atoms sharing electrons. It's saying that I've got atom number one and I've got atom number two, and both of those atoms are looking at themselves like they're like the same ionic issue. One atom is looking and he wants to be complete, and the other atom is looking around and he wants to be complete, and they realize that, you know what, if you give me your electron, then I'm going to be complete, but you won't. Because see, in an ionic compound, the ions realize that the first ion realizes that he's not even an ion, not yet. In an ionic compound, you got two atoms, and one atom realizes that he would be happy if he got rid of an electron, and the other atom realizes he would be happy if he could get an electron. So that first atom gives the second atom his electron, and that turns both of them into ions. And then thanks to ionic bonding, it forces the two opposing charges to attach to one another. Whereas with a covalent bond, you wind up having these two atoms where both of them need electrons. Neither one of them can spare giving their electron. If they gave their electron, they'd cease to either be whatever element that atom was from, or they'd cease to exist. So they can't do that. So both atoms need electrons, and so what they do is they come to the thorough agreement, let's just share. Henceforth, the picture down here with my man feeding the tiger. The tiger would love to say, hey, I'd like to, eat you too, but, it'd be a lot easier just to eat from your bowl due to the fact that you're going to take care of me. I need someone to take care of me, and the monk actually needs the companionship. They both need something. All right. So you'll notice that on this slide it says 4 elements of the human body form covalent bonds. Most commonly, oxygen, carbon, hydrogen, nitrogen. You'll see this in our second session when we discuss organic compounds and organic molecules. When we talk about organic compounds, you're going to find that they always have oxygen and carbon and hydrogen in them, and some of them even have nitrogen in them. The bottom line is that they're going to have these types of elements that like to form covalent bonds. They share. So when you look at, for example, a hydrogen molecule, that's formed from 2 hydrogen atoms. Remember what makes a molecule, right? What makes a molecule is when you have 2 or more atoms and they attach to one another. All right, so you make a molecule. So in this case, I've got these 2 hydrogen atoms. In order for this hydrogen atom to be complete, he would need 2 electrons. That second hydrogen atom is not going to give up his electron just so that hydrogen atom can floss 2 electrons and then that other hydrogen atom can cease to exist. He's not going to do that. So what's going to wind up happening is they're going to say, hey, you know what, if we get close enough to one another, we can have our electrons in the same space. And because they're in the same space, we'll be sharing electrons, and it'll be just like us both owning the electrons, but we're just sharing it. It's kind of like I had a roommate a long time ago when I was in college, and I had a video game system and no games. And he had games, but he had no game system. So we had to make a deal, and it was the funniest deal. It's something we laugh at now, now that we're grown and we can afford to buy the game and the system. But back in those days, we were broke college students. So what was interesting was we had to share our resources. He had the games, I had the system. Never once did we say this was my game or my system. We just said this is our game and our system, and we shared it because we were living in the same apartment. So it was all in the same space. It was all set up in the same spot. You can see this methane molecule down here. That carbon really only has 4 electrons out there in the outer shell. The hydrogens all need a second electron to fulfill their little octet rule out there to fulfill their full their full ring, their full orbit. So what winds up happening is they share with that carbon, so that that carbon feels that he's full with 8, and so that those hydrogens feel that they're full with 2. And then probably the most common, most well-known covalent bond within a molecule is H2O, which you can see here. The oxygen really would like to have 8 electrons. However, the hydrogens would love to have 2. And so what they decide to do is just come in really close and share electrons, so that at any given time that the electrons are floating around, it's almost as if the oxygen actually has 8 electrons orbiting it, while the hydrogens feel as though they have 2 electrons orbiting them. Okay, the last thing that we want to talk about in this session is dealing with acids, bases, and pH. And really, to be honest with you, once you grasp an acid and a base, then you really get a chance to really understand where we're going. Acids, usually the first thing that people learn about acids is what they see on cartoons or video games. Henceforth, the picture of not Scorpion, how dare I? Scorpion is one of my favorite characters on Mortal Kombat. You'll see Reptile from Mortal Kombat series. Over here to the right is actually the classic Reptile outfit and character. And Reptile has an attack where he spits acid from his mouth. And when you see the cartoons and the video games and even the movies, when something's shooting acid, it's corrosive, it burns through everything. And so the question comes up, okay, if acid is so potent, then what's it good for? Well, hydrochloric acid in your stomach helps to denature and break down proteins in your stomach. That's one of the primary jobs of the stomach in the first place, is to help you digest protein. So when you send that piece of chicken or pork or beef or fish down into your stomach, the beans, legumes, all those things that have protein in them, when you send them down into your stomach has to produce stomach acid or gastric secretions to help break down that protein. Now, if you stuck some acid in water, what would happen is it would dissociate. In other words, it would pull apart. That's what dissociate means. It means when something pulls apart, falls apart. The acid would fall apart, pull apart in water, and it would release a hydrogen ion and an anion. Now, remember, a hydrogen ion is positive. But the thing about it is that I'm looking for something. I thought I put that slide in there, but I don't have it in there. But let me back up. So you drop the acid in the water, it dissociates, and you drop off a whole bunch of hydrogen ions in the solution. And when you drop off those hydrogen ions in the solution, it tends to change the game. It's going to change the way that a cell is going to respond. It's going to change cellular activity. It's going to change chemical activity within the cell if you add a whole lot of hydrogen ions to a solution. So when you start talking about acids and some different clear properties of acids, I kind of borrowed this to Purdue from Purdue University's. Big shout out to the biology department and chemistry department out at Purdue University. Purdue says that there's 4 characteristics about acids. Acids, generally have a sour taste. You've noticed that when you taste vinegar, or you taste some type of lemon juice, or when milk starts to spoil because the bacteria in the milk is starting to produce lactic acid from eating all of the milk sugar. That's a key about acids. They have a sour taste. Number 2, acids are corrosive. Henceforth, why when you see a truck with acid in it, or you go by a plant that has acid in it, or you're working somewhere where it has acids in a container, you'll notice that the sign that denotes that acid usually shows a test tube pouring something out, and it shows that pouring thing hitting someone's hand and a piece of that person's hand missing. That is trying to show that that substance is corrosive. It will burn through something. Oftentimes they use acids to clean off certain things off of metals, or not clean off of metal, because some acids can burn through some types of metals. Acids change the color of certain veggie dyes, such as litmus, from blue to red. That's why they do a litmus test. They'll walk in, take the litmus test stick or paper, and stick it under your running water, and they test the water. And if that litmus test comes back red when it's been running under your water, that's a problem. And then acids lose their acidity when they're combined with alkalines or bases. And that is because when you stick an acid with a base, remember, an acid, it's one of its key things is it releases hydrogen ions, and that changes the whole game. Well, bases, what they do is they release hydroxyl ions, or they release these hydroxide, or not hydroxide, but hydroxyl ions. And these ions, these OHs, bind to the hydrogen ions of the acid, and then they form water. And just as a side note, water is neutral. Water is neither acidic nor basic. It's neutral. It's at a pH of 7. So, when you have water, it's a win-win situation. If you don't need something to be acidic, and if you don't need something to be basic, it's perfect. So if you add a base to an acid, the hydroxyl ion and the hydrogen ion from the 2 chemicals, the acid and the base, they'll join together and they'll form water, and then you'll lose the acidity. It'll actually become more basic. Bases, they like to use their hydroxyl ions to attach to the hydrogen ions, and they remove it from the solution, therefore just making water. A strong base, example of a strong base is bleach or ammonia, which is definitely some strong stuff. So you can't just say bases are the best thing ever, and that you need a base over everything else. You don't necessarily want to say that, because I don't think you want bleach running through your veins. That wouldn't be healthy. So when we start talking about why that's important to pH, we say, okay, so what do we have an acid for? Well, we usually have an acid for its properties that allow it to break things down, like the fact that we use stomach acid to break down protein. But then we have bases like bicarbonate. Those things are basic. They're alkaline. They help to neutralize acidic environments. So we have both of them in our bodies at the same time. Some things you have to understand about bases and acids in concerning the pH. Considering the pH, a pH What a pH is a pH scale, or the pH of a solution, is nothing more than the measurement of how many hydrogen ions you actually have in a solution. So if you have a whole lot of hydrogen ions in a solution, then the pH is going to be very low. If you have very little hydrogen ions in a solution, then your pH is going to be very high. And I'm going to explain that in just a moment. If you look at this slide here, you will notice that as things get more and more acidic, the pH value goes down. So if we start here at 7, which is very neutral, and that's pure water, it's at 7. As we add hydrogen ions, everything becomes more acidic. But as we take away hydrogen ions and add more hydroxyl ions, this pH becomes higher. So you notice bleach is at a pH of 12. It's pretty high. But lemon juice and stomach acid have a really low pH, right here at 2. What we are measuring is we're looking inside of a solution and seeing how many hydrogen ions are actually in there in comparison to how many hydroxyl ions are in there. If there's a whole lot of hydroxide OHs in here and very few hydrogen ions left, then it's going to be very basic. But if it's the opposite, then it'll be a lot more acidic. Your blood is at about 7.35 to 7.45. It's right here. So you'll notice that the human blood is actually slightly basic, because neutral, which is nothing, is at 7. Your blood is at 7.35 to 7.45. And the reason why it's slightly basic is for all of the acidic waste products that your cells actually dump into the blood, making the blood slightly acidic. And a slightly acidic blood is not healthy for you or your body. So you need that. You need those bases. You need water, and you need bicarbonate ions, things like that, to actually help to act as a buffer to neutralize that acidic solution. So you've probably looked at these numbers and you said, well, wait a minute, I don't understand these numbers, Mr. Nixon. 10 to the 14th power, that looks pretty doggone high to me. Well, it's not 10 to the 14th power, it's 10 to the negative 14th power. And if you remember old school math, back on the number line, 0 is bigger than negative 6. Because remember, as the number gets less, as the number approaches 0, the number is actually bigger. As the number goes away from 0, the number is actually smaller. So negative 6 is way smaller than 0. And what's happening is negative 6 is less than negative 5, which is less than negative 4, which is less than negative 3, which is less than negative 2, which is less than negative 1, which means that if this number is getting bigger as we approach 0, that means I am increasing the concentration of hydrogen ions in the solution. But if I'm going the other way, then I am decreasing the number of hydrogen ions in the solution. And that, my friends, is about all that we're going to talk about for today. What I want to do is I want to pick back up next time, and I want to talk about macromolecules, and I actually want to tackle some general characteristics about these organic molecules: lipids, carbohydrates, nucleic acids, and proteins. So that's all I've got for you guys for today. We'll go back and we'll check some things out. Next time, we'll make sure that we get in here and we knock out the macromolecules, talk about just a little bit basic information about macromolecules and how they apply to anatomy and physiology. I'll talk to you guys later. Peace.